Thank you. Hello, everyone. Make yourself comfortable. Make sure you have a coffee. I would like to talk a little about microcontrollers and what we've done with that. I'm a software engineer working on Qt for the past 16 years. Not tired of it, and quite enjoying those little thingies here. So a little bit about the reason why I'm here. Oh, before I do that, if you have any questions, please raise your hand. I love to get questions. I love to get them in between, so you don't have to remember until the end, this is what I wanted to ask. So if you have a question, raise your hand, and then Alex will chase you, and I'd love to take those questions in between. So don't hesitate to raise your hand if you have them. Maybe not yet, but a few slides further down. Anyway, the background for my presentation is that there's this unstoppable trend of microcontrollers and computers with displays sort of kind of creeping into our life. From ticketing machines, payment terminals, all sorts of appliances at home, ovens. They're all getting displays nowadays to show things. They're all getting touch displays. And I mean, there are even toothbrushes out there with an LCD display. The LCD display shows you how well you've brushed your teeth. I mean, toothbrushes. So even those things are getting microcontrollers. And people expect good user interfaces on these things. They expect them to work just like your smartphone. And that's sort of a difficult thing to achieve because they cost like a factor of 4 to 5 less, maybe, than a smartphone, than an embedded, like an MX6 or something like that. But they're hard to program, and it's hard to get that kind of experience. You need to know a lot of low-level APIs. You need to know a lot about how the hardware works and how the displays work and how to get most out of it to really get a good user experience on those cheap devices. And, well, that's kind of what we're in the business in. We want to make the programming of these things easier. We want to make it more fun for you to do that. And that's kind of why we are also in this whole area, and that's why I'm personally in there, because I truly believe that programming should be fun, and we can make it easier, and we've been on a good way with Qt so far, and I think we can do the same thing here. So for microcontrollers, we've been doing this for a while, but it was really end of last year, beginning of this year, when we went back to the drawing board and we realized we're not quite there yet. We can't really meet the memory requirements and performance requirements that we really want to have to get something really, really good and small. And so we went back to the drawing board and we did something new, and about 9 months later, well, here we are. We have a new graphics engine for microcontrollers. We call it Qt Quick Ultralight, not just light, but ultralight. And we've got a lot of stuff in there. We've tried a lot of new techniques and things that we haven't done in the rest of Qt yet, and we've packed it all in this thing, and I want to show you these. I want to show you those different little building blocks that we have built into this project, into this engine, to give you an idea of how this works. I'm a firm believer in the idea that when you use a piece of technology, you have a rough idea of how it works. It makes it much easier for you to diagnose problems, to diagnose performance, and to get the most out of it. And that's really, really important, right? To get the most out of your toothbrush, maybe. So, quick outline. These are the building blocks I want to touch in this presentation. Happy to diverge a little bit if we end up with questions somewhere else, but this is sort of the rough outline. I want to first give an overview of the general kind of workflow and what we kind of expect and what the environment is like. And after that, I want to dive right into the event loop. This is something that works different than when you run under embedded Linux. And I'd also like to explain a little bit of the rendering. This is also something that works different than what Qt Quick normally works. It works it's something I realized afterwards. It works much more similar to how Graphics View actually works. The author of Graphics View is sitting down here and he's smiling. So you'll see this is a bit a different rendering technique. And after that, I'm going to look at how we pack resources into the whole thing. So how not only we produce graphics, but how images, translations, etc. come into this. We've done a completely new approach for this, and I'd like to show you that. Yesterday, Lars in the keynote also mentioned a property system, that we are redesigning the way we do properties and property bindings in Qt. And we want to do this for Qt 6, but we've already done it here. This is actually where this originated from. I'm going to give you a sneak preview of that. But on that topic, Lars has a technical presentation at 2 o'clock, I think, here in this room, where he goes into even more detail of this. And finally, I want to show you this compiler that I mentioned yesterday briefly for compiling QML code ahead of time, the actual code itself. It's quite an exciting way of generating C++ that, for us at least, is completely new. So I'm going to dive into that as well. 1, 2, 3, 4, 5, 6 topics, yeah. So let's start with the overview, briefly. I'm going to make we all have the same assumptions, I hope, that your application consists of some C++ code. We also give you the ability to use QML, the way you're maybe used to it. Images have to be part of it. Everything is graphic nowadays, so there are going to be images, and eventually your toothbrush will have to show you maybe the time, how long you brushed your teeth, so you're going to show text. Text is rendered using glyphs, and glyphs are in fonts, and we assume that your application is going to have TrueType fonts. We can also pick them up from the system, but fonts are an essential resource to the application. And unless you target really only one language altogether, but rather something international, translations are intrinsic to this. Something that often comes rather late, but it is really, really important to have to be able to ship to international markets. On translations, we have kept things pretty much as they are. So the same tools, Qt Linguist you can use, and lupdate to extract translations. So nothing has changed from a developer perspective there, but we've changed the way we do the translations in the inside. I'll show you a little bit of that. So those are the application building blocks, and then afterwards, those need to be sort of pushed into the build system, the thing that nobody really, or a few people only really like, but everybody has to deal with. We have chosen CMake as the build tool for this, because the majority of C++ developers know it and are familiar with it, and it does the job really well. So if you use Qt Quick Ultralight, you're going to use CMake as the build system. We provide you with integrations in CMake with the functionality, with functions in CMake to do certain things, to inject QML files, etc. Eventually, CMake will call the C++ compiler. We will take care of picking it up from the SDKs that the board vendors typically provide. So we provide CMake toolchain files to pick up the right compiler, etc. And then we have a bunch of other tools that take care of images, fonts, and QML files. Here I've just labeled it as just QML compiler, but we've actually got a bunch of different programs that the build build tool will call to process and to compile the QML side of your application. We are also assuming that everything will be finally linked together into one static binary. We also link in some support libraries from Qt Quick Ultralight, but eventually everything is coming together as one static library, or sorry, as one static binary. So there's one image that comes out of it, and then that is the image. There's no extra dependency, no extra libraries, etc. This thing even has the new lib C runtime, or the bits of it that you use, linked into it. So all of that comes together into an executable, sometimes a hex file that describes where what goes. And then you have to flash it onto the device. You can do this from Qt Creator. We also provide you with makefile targets to do this conveniently. But we assume that this image will be flashed onto the device. Certain segments of your binary will end up in different areas. So code ends up in certain areas. Data segments end up in certain other areas. Images may end up somewhere else, because you have this interesting pattern, this interesting effect on microcontrollers that certain areas have different performance characteristics when it comes to accessing it. So there can be areas in the RAM that are very fast to access from the processor, because the processor caches them, but they're slower to transfer to the frame buffer, to the area that is later then showing up on the screen. On the other hand, there are memory areas that are really, really slow to access from the processor, but they're very, very fast to access from one of those graphics accelerators. They can copy those very efficiently. So we give you a bit of control, and we make use of the ability of those device characteristics to get the most out of the best performance, basically, out of it. So images end up usually in different sections than, say, your data structures or your code, for example. Right, but that's sort of the rough idea. When all of this is flashed onto the device, you're going to power it on, and hopefully everything will work. The processor will start at a specific address running, and this is, in fact, where we placed some initial board initialization code, or that comes from the board SDK. That takes up really, really basic things like setting up the clock, initializing RAM controllers, memory mappings, etc. We take care of all of that, or we take care that this part works at least. So as a developer, you don't have to worry about that. This is part of this low-level programming that I mentioned earlier that you shouldn't have to deal with, and you don't really have to deal with unless you'd like to. Some people like to, that's fair. So once we're at that point, we're going to, in a normal Qt application, when you enter main, that's when you usually run Qt application exec to enter the event loop. And that's a bit I want to look at now, because that one is quite different, how it usually works. When you have an operating system, it's different than when you run on bare metal. So we're talking about, at the moment, of running Qt Ultra on bare metal, on no operating system, no nothing. We are working on also allowing you to combine this with real-time operating systems, like FreeRTOS, for example, or RTMS. But while that is still work in progress, I'm talking only about the bare metal setup right now. And the bare metal event loop is something that is quite important when you look at devices that run on batteries, power consumption. You'll see why. But the event loop in this diagram, it starts with something quite boring, which is putting the processor to sleep. So our event loop starts with an instruction that is called wait for interrupt, WFI, on ARM processors, and all it does is it puts the processor to sleep. It's kind of boring, but it's really important, because once the thing goes to sleep, it doesn't really need electricity so much anymore, or only very, very little, if any. And it waits, like the name says, for an interrupt. So interrupts are external triggers that have the ability then to interrupt, or in this case, when it's in this state, to wake up the processor to do something. There are all sorts of different scenarios that can trigger an interrupt. Simple example, because we talked about touchscreens, I'm touching my screen, right? That is an external event, and that I want the processor to wake up so the processor can react to it, can do something. I'm tapping on a button, I want this button to change its color or do something else. So I need to wake up the processor. The processor does wake up, and we provide, for example, a handler for touch events, and we receive data. There's not a dedicated touch interrupt on the controllers. Usually that goes through a different serial bus, but for the sake of simplicity, I'm saying there's a touch interrupt. That's where we read data from the touch screen. Where did you touch? How many fingers? Which areas, etc. And we collect that data, and then we quickly post it into the event loop. And then we return. There's another kind of interrupt that we also take care of setting up, which is a timer interrupt. We typically set it up to fire every millisecond. So every millisecond, the processor will eventually wake up. And all we really do in that thing is we just increase a global variable that counts how many milliseconds have passed. This allows us to know where we are in animations, etc. So those are two examples. They are different. If you connect different peripherals, etc., they can. If you have an Ethernet controller attached, so that one might wake up the processor if a frame was received or something like that. But those are the two ones I'm talking about here. In Qt Ultra, you will be able to also define your own interrupt handlers and integrate them into this event loop and post your own events and react to them. Or we provide defaults for these too. So after an interrupt has woken up the processor, it's going to come back from this instruction that we originally ran, and it's going to resume running code there. We call this the wake up. So even though the processor has actually woken up earlier because we've done something, now in our event loop we are woken up. We assume that there is something to be done. And that is typically the case. Like when I touch something, I posted data with touch-related data as a touch event into the event loop. We're going to take that out and process it. So for a touch event, that, for example, means finding the item that you did touch, finding the item that is under the finger, and notifying that item, and then maybe running some code that you have specified that when this button is pressed, some business logic should become active. Another thing we also automatically do after we've processed any pending events is we also look at animations. So animations that are defined as in 3 seconds, this element should move from here to here. So given the timer that we've counted earlier, we can see where we are now in our animation and how we need to move our item further, need to change coordinates, for example, or scale factors or dimensions, etc. But this is where we process the declaratively specified animations in QML. And finally, this is all non-graphical. Finally, we can't avoid it anymore. We have to produce pixels onto the screen, so we're going to start painting stuff. That is the last step, and this happens since we get woken up at least once every millisecond. We don't always paint something, but at least every 60 milliseconds, we do end up painting onto the screen so that you get 60 frames per second. Painting is quite interesting on these things. You have a memory area that you say is my frame buffer. We typically allocate 2, and then you tell the display controller, hey, what's on the screen, show it from this address. And then you prepare the next one, and then you tell it just, hey, now you show it from this address. It's like a pointer that you direct. It's an interesting low-level way of rendering, and you can reuse what's in between those, so you don't always have to start from scratch. Anyway, we get back to that a bit later, or quite soon. But this is roughly how the event loop sort of looks like. So we put everybody to sleep, then we wait for to consume no electricity, and so that you can run on batteries. And then we act on it, and then finally the typical steps of the event loop that are quite similar to also how Qt works on embedded devices kick in. So let's look at the next step, the last step of the event loop, which is the painting. I want to briefly touch on how we render things onto the screen. First, I want to take a sip. So imagine a scene of QML items. There's always a root item, right? Let's assume in that root item there's a rectangle, and inside the rectangle there's some text, and let's assume there's also an image somewhere. Maybe that rectangle looks like a button or something like that. But it's a very simple scene, like you know it from QML. You construct this, and this creates a hierarchy. This creates a tree of items, as we call them. And so we have the objective now to represent them onto the screen, to visualize them in a correct way. There may be items obscuring other items. There may be items not visible at all. So there's a certain amount of work that we have to do. This is what I'm going to go show you now is a very simplified diagram of kind of the rendering algorithm. And it does a lot of things that we don't do when we render with OpenGL typically. So this is a bit different. We do a lot of do more manual work. It's a bit more like the graphics we used to work. So one of the things we do is we compute which areas on the screen actually have changed. If I have a large scene and I press a button, I tap on a button and that button changes its color because I put my finger on it, then I really only need to redo the pixels in that area. The other stuff I really don't need to touch. It might be, though, that this button will also trigger some spinning animation somewhere else on the screen. So suddenly I have 2 areas. And typically we represent this as a series of rectangles, a series of rectangular areas, and we compute that list of rectangles because we call them dirty. Those need to be redone. Typically that's less than the entire screen, so ultimately we end up writing and producing less pixels than the entire screen, which saves us time and gives us performance. Another thing we do at this early step as a preparation is that we compute which items are obscured by others. So an opaque rectangle in a green color will hide anything that is underneath. So if there's text underneath, that text won't be visible. So we spend a little bit of time to compute which areas are obscured by opaque items in your scene. This allows us to skip rendering of entire items altogether. But those are the two preparational steps, and then we can finally enter our final recursion into this tree that is on the right-hand side here. For me, it's on the left. No, it's lower left for you. So we go through this tree, and we start looking at each individual item. Items have children, so we look at the item itself, and then we look at the children. And if we can determine, based on the data structure that we built earlier, it's a small BSP tree, if we determine that this thing is underneath another item, and it will not be visible, well, then we don't have to do anything. We skip it. And that allows us to save a lot of work. And it's also a common pattern anyway that you have items hidden, and then they only show up when you start an animation. So this can help a little bit. Also, if something is just not, it just hasn't changed, we know this is not touching or intersecting with any area that should be changed, then we can avoid a whole bunch of work as well. So those are the two primary kind of escape conditions that allow us to avoid further work, but eventually something will be visible on the screen. And so then we have to look at what it is that we should render. There are different primitives. I call it render image. We call it in our code, we call it rendering image and rendering text, or rendering a rectangle. But let's take another look at that. Or let me explain a little bit more about it. I call them rendering primitives. It turns out that all of those 2D user interfaces, they can be really, in terms of primitive rendering, can be simplified very much. And I'm going to say there are two types of operations or primitives, is drawing rectangles and drawing textures. Now, a rectangle is just a shape. So what I really mean is that it's a rectangular area that is where the color of each pixel is determined by the same color. That can be either a fill color, say a green rectangle, that everything in that rectangle should be green. Or if it's a blend operation, then I might say, I have green as every color for every pixel, but I want that green to be blended with what is underneath, and that can be different. But both of it is basically what we call filling a rectangle. And then the other primitive is drawing a texture, so where you don't have just the same color for every pixel, but you have a different color for every pixel, depending on what the image is. So this is color textures is another name for images, basically, ordinary images. Images of smileys on your toothbrush that shows you've brushed your teeth enough or something like that. But if you show text, it's a special kind of image, and we treat this specially. That is called an alpha map. So that's a texture that only has transparency values. This is a very efficient representation of glyphs, which you use to compose text. Otherwise, when I say color here, I always mean red, green, blue, and an alpha value, so RGBA. But for alpha maps and for glyphs, we have only one value, which is a transparency value. And we combine that with the color of the text that you would like to use. And that's how you blend these two together with the background to produce colored text. There's a special case, which is transformations. I've made this special because this typically involves, in our code base, a lot more work, because it makes things more complicated. If you just have a plain rectangle, it's fairly simple to get that onto the screen, but once you start applying transformations, it gets a little bit more complicated. So you can start rotating things, and then you have to do, your geometries become more complex. You have to suddenly start rendering lines, and you have to find intersections. So in our code base, this is a special, slightly slower code path to do that. And even there are some things that are fast again. So if you do 90 degrees rotation, that's usually easier to deal with. But transformations can be expensive. So we don't do all of them because it would be really, really slow. But the common kind of transformations we do. But really, everything that you see on the screen, also in the demos downstairs on the booth, on this beautiful round watch face, etc., it's basically filling rectangular areas with either colors or images mostly. It's that primitive, but it helps at least, I think, to think of it like that. The magic is, of course, composing this in the right order with the right dimensions. That is what makes the user interface finally the beauty that you can see. What also makes it beautiful if it actually runs smoothly, if it's fast. That is something that typically requires a bit of help. So on those microcontrollers, they're not very fast. We do everything in software. We have everything implemented in a way that is a reference implementation and that produces the correct result, and that runs on the microcontroller itself. But while the main processor is busy producing those pixels, blending those rectangles, etc., it can't do anything else. And it's kind of a shame, and especially if your scene is complex, that can really bring you down to very few frames per second. So fortunately, the people who make these microcontrollers, they've been in this business long enough to understand that they need some help. They need to add some help there. So they offer typically extra dedicated chips that provide you with functionality to do graphics in a faster way. So those earlier operations that I've shown with those rendering primitives, they have help for that. What those chips usually do is that they allow you to do, it's kind of like copying memory. All they do is copy memory. They can copy memory areas from one area to another. Typically, that means copying images. But they also are not just another memory controller or DMA controller that copies memory. No, those chips are typically aware of graphics a little bit. So they often know about blending modes, ported blending operations, for example. So you can say, copy this memory area into this area, but also apply this transformation at the same time, this blending mode. They can also do solid fills of rectangles typically, and some of them can also do transformations, scaling. Sometimes they can do 90-degree rotations. And the beauty of these things is that this can happen asynchronously. So you can batch up these operations and say, by the way, I want to copy this, and then you send it off to this graphics chip, and then the processor can do further work. It can continue recursing through this item tree, for example, find other items that are not obscured, for example. And this really, like I said yesterday, this really makes a difference between crawling around 15, 20 frames per second or really hitting the 60 frames per second. So we have implementations at the moment. We have support for 3 different accelerators. The PXP that is on the NXP family of devices. We support the Chromat on the STM devices, and we have what's it called? R2D2 or something implementation for the RH850. It's an automotive, kind of an obscure automotive chipset, but we also have that. But that's just the base of it. We want to add more. We're going to have to add more, or support for more accelerators, graphic accelerators. But we've got 3. That's a good sign that the interface we have in between them works well enough. That's sort of a rule of thumb we have in Qt, is that if an interface works for 3 different implementations, then it's probably good enough. Then it's worth something. So we're going to add more, but we already support the typical stuff out of the box. So we can get stuff onto our device. We can react to touch events and timers. We can hopefully produce pixels onto the screen. But your user interface is not just going to consist of solid colored rectangles. There'll be other stuff. There'll be images, for sure. There'll be text. You'll want to have translations, different text depending on the language, etc. So let's take a look at a little bit how we handle that in Qt Quick Ultralight. This is a reminder for me to switch to Qt Creator, because this is something I like to rather show in Qt Creator itself. So this is sort of the minimal. This is the minimal kind of hello world in Qt Quick Ultralight. It's a rectangle, the kind of QML you know, but we added support for a special keyboard, pragma main, that allows me to skip the boring work of writing a main function. But the build system will take care of doing that on the side as well. So you can start a QML application just with a QML file. This is your root item where there's pragma main, and that's it. And because we like to do things in Qt, I can demonstrate it without a microcontroller as well. We have a backend that uses Qt itself to show it on the screen. This is very convenient for debugging. So this just produces, as you can see here, a green rectangle. What is interesting is how this looks like now. First of all, let's look at what we generate for this. So the file is called, you probably can't see that, it's called demo.qml, okay? So keep that in mind. This file is called demo.qml. I've got a CMake list txt here. That is fairly straightforward. I have a QUL, that's how we call the CMake package, Qt Quick Ultralight. We have an executable. And we have a function in our CMake API that says, like target sources, but we call it target QML sources. This is where you can associate QML files with your executable. We have also a function for embedding translations. This is where you specify the TS file that you would like to have associated with it. And you can have multiple, obviously. And finally, we have to link something together. And when we compile this, when we instruct CMake to do its job, we compile this QML file, this demo.qml, into a header file and a CPP file. So the header file looks like this. There's a beautiful auto-generated code warning, very important. But what's really interesting here is that we've created a struct. This QML item is just translated into a plain struct. That struct subclasses a rectangle. That's kind of what we semantically expect, and it's got a constructor. So if I just show you how far this goes, if I add another rectangle in here, and maybe I add another item, just like that, and we recompile it, our struct has changed, and it's got two members. Let's see if I can show this. So you can see there's another rectangle. Something could be inside this data structure, but there isn't. And this is a member. So when I instantiate this demo struct, I also at the same time instantiate the other rectangle I specified in the item. It's all done in one go. There's no extra memory allocation involved. If I allocate this demo, I'm done with everything else. This is quite an efficient thing to do. And this goes down to nesting. So this changes a little bit. You think this changes a bit semantics. You can't just take an item out and move it somewhere else later. But in practice, this is really not an issue. But this allows us to very efficiently avoid memory allocations when instantiating items in QML. But back to the plain rectangle. If I look at the CPP file, look at the bottom, there is our main function here. And this is where we create our demo, our QML item, our root item, in fact. So that's just allocated in read-write data, and we have an application object that we notify, by the way, this is our root item. This is all generated code. But you can see this is cooking with the same ingredients that we cook in Qt typically, or that you can also cook by hand. There's also a concept of a language property, but I'll show that a bit later, that we set. But this is basically what we do. And then the color that we specified is set here as a property. So remember, the demo is a rectangle. I'm following that one. And the rectangle has a property color. That's just another C++ member. So our constructor of demo, where we earlier said this shall be a green rectangle, well, this is what it does. It's the alpha value, so it's opaque, red, green 80, and then blue. Let's change this to an image, because I wanted to talk actually more bit about the resources around this. So let's talk about changes to an image. Changes to an image. Images don't have color, that's fine. So we do a Qt to yes logo.png. I think this should work. Yes. And if you run it, well, we've got maybe I should have picked a newer image, but we see that this is clearly coming from an image. So our header file hasn't changed, well, except for the fact that now our root item is derived from our image. And our CPP file, however, there's stuff in there. Numbers. And it turns out that's the image. We've taken the image that you specified and we've embedded it right into the source code. Let's start at our constructor again. The source property that we've set, that was a file name. Now this becomes what is that? A raster buffer? You could probably guess that this is basically not a string, but this is actually kind of a pointer to the image data directly. So there's no extra image loading necessary, but we've got a pointer to an image. And this raster buffer, if I follow the symbol, this is again a structure, a static variable, a global variable, but it's read-only. And it contains predetermined, pre-processed image data. So we take the image that you specify and we look at it and see, okay, this is a 32-bit image, but the target device has only 8-bit per pixel, so we might as well dither it, for example, at compile time. Or we can find out that the large image that you have, it turns out it really has only pixels in the between, and the rest is just It's transparent. So we will process this down to a lot less. We will only embed the real data that has pixels. We can do this even on multiple regions. So if you have a large image with real data here and here, the rest is transparent, we'll just embed those two sub-images, basically. But when you use images, we don't load them dynamically and have some file name. No, we look at the file name at compile time, and we look at the image you're pointing at, and we're going to go ahead and embed the image right away. So it's embedded up here, line by line. This looks like line pointers here, and then here comes the actual image data. I think if I was able to zoom out, like maybe I could see the World Summit logo, I'm not sure. But this is what we do with images. We go ahead and we compile those and process them at compile time. We decode them also. This is another point. At the moment, we decode them because at least the devices we have downstairs, they don't have support for decoding compressed images. So the PNG files or JPEG files, we decode them and embed them here. But the result is that when you render, let's go back to something that looks a bit better. When you render a user interface and you have those images right there in memory, all you really need to do is just copy them. So a lot of the UI producing work is copy images from one area, from the same area, onto the screen, onto the frame buffer. And by not having to do any other processing, that can be done very quickly. I had images. We can also have text, of course. So let's do text. Hello world. And let's do it with the color white. This should also produce a white text. Yep, there it is. For text, there's nothing really different here. This is the string here, hello world. Oops, sorry about that. There's the hello world string here. And this text, if you follow this property, this is really just a string property. But if you look at the CMake files, you will notice that we have generated another file. If you look into what the build tool generates, and that's called Qul Fonts. And what we've done here is that we have generated a lot of stuff again, and this is the font that you're using. Or rather, these are the glyphs. These are only the alpha maps, the glyphs that you're using. We also embed kerning tables, etc., so you can kerning correctly. And we have a character map that allows us from characters to glyphs. But ultimately, we embed only those glyphs from the font that you're actually using, and everything else we ignore. We don't do that. So this gives you a static text, but it gives you something that is very, very efficient. There's another special element that is called static text that we provide, where we just embed the glyphs directly, so we don't even go by strings anymore and map it. Okay. Maybe the last thing to show would be translation, so I can do a QSTR here, and then if I compile that.
There's a question here.
There's a question. I apologize, I didn't see that.
Hi, just wanted to ask what image format do you support there?
I'm sorry, I couldn't.
What image format do you support? Only
What image
PNGs?
format
Yeah.
we support? Well, as a source, we support anything that Qt can read. So PNGs, JPEGs, you can extend it to different kind of image formats.
Yeah, no vector graphics or no vector graphic image, or it's only rasterized? Only PNG, JPEG?
I apologize, I can't understand you.
Yeah. You only support PNG, JPEGs,
WebP,
no
whatever, you
vector
can add more image formats. It doesn't really matter in the sense that you can write your own image handlers, as long as we can decode it into a Qt image, and then we'll embed the undecoded image data.
Okay.
So we're using the standard Qt image loading for loading the source images. So we're not limited to those, but it's fully extensible. Okay, quick look at the translations. I added TR, and suddenly our generated code will contain an array called translation. And this is where we have the translations embedded that you're using right as a string. So this is the German translation. Hope you recognize that. And then this is the English word. And so when we use that string, we will end up pointing straight into this array that contains only the translation that you use. So this is how we handle translations. You specify at build time what translations you want, and we'll embed them right away for you. You can use multiple versions of your image. You can create an image for France, an image for Italy, an image for Germany, and include those. Or you can build one for the entire European region, include multiple European languages. but they'll be just embedded as strings, UTF-8 encoded strings in the code. Okay, let's go back here and go back to the slide. So to summarize, images, fonts, and translations are something that we treat very differently than Qt typically does. So in Qt, images and fonts and translations are loaded at runtime on demand. Here on the microcontrollers, we have no file system. We don't want to spend any time on doing these things. So images, we decode up front. We embed only the bits that are necessary from the images. Same goes for text. We embed only the glyphs that we need. And for translations, you get to choose, and then we embed the strings of the translations right away. Question there?
So hi, Simon. So I'm wondering, what about text that's bound, like a dynamic text? What if text is composed by adding things together, like numbers plus text? How do you ensure that all the glyphs get included?
This is something that is sort of work in progress, but the basic idea is that you can say, I want to include everything, or this is the character range. These are the ranges we want to support and we want to embed as glyphs, and that's so that you can still concatenate strings dynamically and be sure that you have glyphs that back up this string. So clearly, if you build something that is not just a demo device, but something that receives a news feed from somewhere else over the network, and you want to show it, you have to have an entire coverage of fonts. And in the worst case, you have to include all the entire coverage of a font. But if you know ahead of time that this device is for the French market with French news to display, then you probably don't have to. You may not have to include CJK character sets, for example. All right. We can do graphics. We can embed all these things. We can do translations. We can do text. But the beauty of QML is that you can express relationships between objects in bindings. And so for that, we've done a completely new binding system. We've experimented with it. It worked so well that we said, we're going to take this right away. I'm going to take only a brief look at it, because I really want to point to Lars's presentation later, also in this room. Have lunch before that. He goes into a detail how this property system works. But in a nutshell for you, you've hopefully seen something like this before, a rectangle with a padding property, and then the height is calculated. The height shall be the product of the width of the rectangle times 2 plus the padding. And we know that when the padding changes or the width changes, we recompute the height by recomputing this expression. And traditionally in QML, this is built on the idea that objects have properties. And classes that are used to instantiate those objects have functions. So you have to declare setters. You have to declare getters, at least a getter, and you also traditionally have to declare a signal that you have to emit, or that is generally being emitted when the value of this property changes. But this all belongs to the class. This all belongs then at runtime to the object. So the object is also the one that is truly responsible for emitting the signal. And this can be tricky at times because it's not always emitted right away when when the value changes, but sometimes due to implementations, it's emitted later. So everything is traditionally very much tied to the concept of those classes. And while that works well, it is not. It can be a bit heavy. It requires a full object model. And in the current way of using the current implementation in QML, when a property changes and that signal is emitted, any bindings that depend on it are evaluated immediately, right away. And this is what we are doing differently. We've tried a different approach. We've made it object-centric. Instead of being all centered around classes and objects, the property itself now has everything it needs to be a full sort of citizen in this world of properties and relationships and bindings. So a property is a template type in C++ for us, and the type is the data it encapsulates, and the property encapsulates the data. The property has the data itself. It knows when somebody wants it, and it also knows when somebody gets it and changes it. So properties also keep track of any binding that queries them. So while a binding, this calculation width times 2 plus padding, while this thing runs and queries the width, for example, the width itself is aware that, so this thing wants to know my value. Okay, I'll give it to you, but I'll keep you in mind. So next time the width changes, I'm going to call you back and reevaluate it. This becomes suddenly an intrinsic property of the a property of the property. This becomes an intrinsic feature of the property itself, not of the object or any parallel data structures. That makes the bookkeeping easier and makes it nicer. So when something changes, we don't immediately reevaluate the binding, we just mark it as dirty again. We call everything dirty that we want to do later. It's weird, but somehow we do this as programmers. So we mark it as dirty, and then later it'll be evaluated only when the value is actually needed. And this makes things a lot faster. The result is that we found out that this property system behaves in practice exactly like before, but it's much lighter. We can avoid many memory allocations, and it's the laziness of it avoids this unfortunate effect of binding storms, where multiple dependencies result in a multiple evaluations of the same binding, even though that's not really necessary. So that is something we're quite happy with, and I again pointed to Lars's presentation later if you want to see some pseudocode. So the last section I want to look at now is that we can do graphics, we can do property bindings, but we also don't have a JavaScript engine. But you want to write a little bit of code, you want to write expressions in QML files. So this is where we have done something a bit more extreme, and we say there is no JavaScript engine, there's no garbage collector, there's no eval, there's no runtime interpretation. Instead, we want to do everything at compile time. We want to generate code that is almost as efficient or as efficient as if you wrote it by hand, except that in those QML files, it's a lot easier to write. So you can avoid a lot of C++ boilerplate with function declarations and the like, and namespaces and colon, and whatnot, and pointers and whatnot. But the beauty of QML is that you can write these small little expressions and these tiny little snippets of code that are well contained. So we wanted to preserve that. And that hasn't changed. So you can continue to write functions in QML. But what comes out of it, that's a bit different now. So I'll try to show you a little bit of that. So let's make a mouse area here. We call it area. Mouse areas have a property that is called pressed. So let's say I want to say this rectangle shall be area.pressed. It shall be green. No, it shall be blue when it's pressed. And otherwise it's green. Now, the conversion from a string to a color is implicit in Qt Quick, which is a little bit magic. So if you do that, the build will actually abort, and Qt Quick Ultralight will complain that you cannot convert dynamically strings. We see that at the bottom, strings to color. So we have to use a slightly different API here. We use qurl.color. This tells the compiler that this string is intended to be a color, not a string. Because what comes out at the left-hand side has to be a color. Oh, this looks terrible on this resolution. Sorry about that. I'll break this. OK, maybe this looks a bit better. So this is the simplest kind of binding expression. Area is pressed. I want the color to be blue. Otherwise, I want it to be green. So we'll check if this works. No, it doesn't. Huh? Oh, thank you. Thank you for the attentive audience. Of course, this was just a test. I knew this. I just wanted to see if somebody... Thank you. OK, so this works. Let's take a quick look at how this, what we do out of this, what we make out of this. So if you look at the demo, there's now a binding functor for a color. This is looks a bit like an obscure data structure, but it's all auto-generated. And this thing has a call operator here that returns a color. RGBA32 is a C++ type for what is the color in QML. So this thing will contain the code that is the binding expression. So let's take a look at that. Ooh, this looks like typical auto-generated code with obscure names and things. But if you look at it a little bit closer, you will recognize some terms. And you can maybe mentally reconstruct this binding expression. So there's a self. R is short for register, because it's a register machine. It's very primitive, but it works. So these are local variables, and the Qt already tells me, Qt tells me that this is a pointer to a mouse area. So there's a self parameter that gives me access to ID named objects, and we've called our mouse area. So this generated line will copy a pointer. Seems kind of pointless, but the compiler will collapse this all nicely anyway. And then it's stored in R2 here, and then from R2 we get it's a mouse area, right? We get it's got a pressed property, and so we get this pressed value, and we write that into a different local variable. And then we check, was it pressed or not? If it was not pressed, then go to label 0. I love goto. There's nothing wrong about it, really. So label 0 is the one here that ends up picking a color which is green. Middle component is red, green, blue. Yeah, green. So it picks green and assigns it to this local variable, and finally this function will actually return it. This doesn't look like particularly beautiful code. We also don't try to make it the most beautiful code, but it's collapsed. It is efficient as if you write it by hand. The compiler knows about all of the types. It knows that we're dealing with colors. It knows that they're being assigned. It knows that there is a Boolean expression that we need to evaluate. And this goes beyond those little things. So I can also write this into I can make a function here, helper function, for example. Choose or pick color, and it returns a color. And I copy the expression in here. I can write functions as well. Now I need a return statement. And here I'm just going to say pick color, because I'm going to use this color picking everywhere else in my application, so I really want it only in one place. This is business logic that is very critical. Now, what is different is that we've done an annotation here. We've said this is a function. This isn't what you normally typically don't do, but now we've said this function shall always return a color. This is a promise. It will always return a color. If inside the function you try to return a string, our compiler will say, no, you can't do that. But if you return a color, it's all going to be fine. And the same goes for parameters. So I can also here put a area pressed parameter. I can give it a bool, and I can call here area.pressed. And now I can use this variable that I passed in. So now the function is fully self-contained. Input is used to calculate the output. And this still works, I think. Yep. But let's look at the code it generates. So now we have a function somewhere here. Where is it? Pick color. Sorry, here it is. So we've generated a function that looks almost as if we've written it by hand. It returns a color, and it takes a Boolean as input from the QML. And the implementation of it is basically what we had earlier as this binding, but this is now a regular C++ function. You can even call this from somewhere else. You can call it from your own C++ code if you want to. You can do that. And the result is that we end up with something, in our experience, that is incredibly efficient. It is super efficient, as if you wrote all of those little binding expressions by hand, except that you don't have to. You can still embed them in the QML file, and you can enjoy that you can see them all on the screen, and you don't have the C++ beauty of lambdas with lots of different kind of brackets, some square, some curly, and have captures. No, you can avoid all of that. We'll generate something for you that is as efficient as that, but it looks as nice as this. If I fix the indentation. So to summarize again, we are quite aggressive at compiling everything ahead of time, including your code, including your binding expressions. We've extended the syntax a little bit by requiring you to specify for functions what the types are. Everything else we can infer. We can figure out that if you have a binding expression that this is assigned to a color property or a string property, so we can figure out that the variable inside has to be a string or you've got to return one. But for functions we can't, so we've changed the QML syntax slightly to add annotations. Beauty of it is that this is also done upstream. We've done this for desktop QML, so this is fully compatible. So if you have a function in a QML file that you share for a microcontroller project and for a desktop project, you can use the same thing there, and it'll work, and it even generates you an invocable meta function that has a nicer C++ syntax signature. So it doesn't take a Q variant, etc. But if you have a function like that with a pick color that returns a color, in upstream QML it It's a function, C++ function that returns you a Q color. Yeah, like I said, properties are already typed, so we can figure out what those means and what's used inside the expression. So we can infer everything. And this is very ambitious, and in the beginning I was a bit skeptical, is this going to work? But it turns out that's enough. We've been able to port huge amounts of example code and demo code over to this, and it works surprisingly well with very little annotations to help our functions, and the rest we can figure out. And the result is much, much more efficient than interpreted, generic, the type can be anything kind of code. This also allows us to detect compile errors, type errors at compile time. They turn into compile errors. And that is, of course, a very convenient feature generally. But the efficiency is for this project, for microcontroller development, was our primary objective. And that works out really, really well. That's how we get to this really, really low overhead. So this covers the building blocks that I wanted to talk about. Happy to talk a bit more, but there's also another presentation coming right after this that talks a bit more about the features of this. Just one last thing, because whoever wasn't there yesterday, we have one release out. Some of the features I showed here, like translations, are not in that release that you can download, but it'll be available. Another alpha will be released very soon. We understand that this is a product that lives from the feedback from users, so we're going to churn out one release after the other. We are ambitious enough that we hope to have a 1.0 at the end of this year, and we want to make many, many more releases. Because this is an early product, but this is also your chance to influence it and give us feedback and make it work. So that's it. Thank you very much. Huh? I have 3 minutes left? Yeah.
Are there any questions?
If you have any questions, you can also ask them now. Oh.
Thank you. Does the event loop take into account if my microcontroller has 2 cores?
At the moment, we don't support multiple cores. I don't know if we're going to do this for bare metal ourselves, because that's a bit of work. So I think the more likely scenarios for microcontrollers with multiple cores is that we're going to piggyback on RTOS support for that. So that we will rely on a free RTOS implementation for that microcontroller to take care of the scheduling and the concurrency issues of that, and then we will build on the tasks that operating system provides. That will be the sort of the event loop kind of. I don't expect us to implement all of those primitives ourselves, at least. But who knows?
To what extent does Qt for MCUs reuse existing Qt code? Is a Q string a Q string?
Yeah. Great question. So this is all self-contained. We think of it as an implementation of Qt Quick for microcontrollers. But the next step that we want to do is allow this to be combined with other Qt modules that implement certain protocols, maybe a Canvas, for example, or MQTT, where we have protocol implementations. And for that, we will take in parts, or our intention is to take in parts of Qt core and combine the event loops, allow us to combine that so that you can combine this. And surely then we'll also do string conversion if necessary. But a lot of the stuff here is also something that we're trying to quite aggressively put into Qt 6, the concepts, so that ultimately the delta becomes smaller. But in the medium term, we want to be able to combine this graphics engine with non-graphical Qt modules under the same umbrella with the same types and being able to combine it.
I have a question. What's the on-chip debugging experience like? Do you have integrations with JTAG like Sega and so on?
Yeah, so integration typically works with a GDB server, and debugging depends a bit how much RAM you have. Can be a bit tight, but I have very positive experience on the NXP devices myself, for example, debugging on those, and yeah, the board vendor typically provided GDB server implementation of some sorts, and that's where we build on with Qt as well.
Sorry guys, we don't have much more time. We need to get going on the schedule, but I'm sure Simon will be around and take your questions if you have them, maybe at the site or something. If there are any more questions, I guess there were lots of questions. So if you could stay around a bit,
yeah,
a few minutes then, and we can go ahead with the schedule. Thank you very much.